All right, so yeah, a couple of more sections too. That's about all I need to say. So let's go back to what we did last time. Last time we were looking at end behavior of these types of power functions, which have whole numbers as their exponents. And we said if we had something like 3x to the fourth, you know what the end behavior does? Just because of what 3x to the fourth, the nature of that. And then we said, well, if we have polynomials, then that leading term, the term with x to the highest exponent, is going to determine the end behavior of the polynomial function. Okay. And we saw that in a couple of different examples of polynomial functions. Remember, the middle portion may have ups and downs, minimums and maximums, local minimums, local maximums. But the end behavior of f of x equals negative x to the fourth plus 4x to the third minus 2x plus 10 is going to be determined by negative x to the fourth. And since that's a negative x to an even power, we know it's going to be pointing down on both sides. The same thing is true for this g of x. Its end behavior is determined by 1/4 x to the fifth. Now, that is a feature of these polynomial functions. And specifically, it's a feature of the graph of the polynomial function. So it's a feature of the graph of a polynomial function. And in 3-4, we just move on with that concept. We're still looking at graphs of polynomial functions. We know that polynomial functions are these functions where we have a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, where our exponents are whole numbers, exponents on the x's are whole numbers, and the coefficients are going to be real numbers so that we can say x to the n is the leading term. We'll assume that a sub n is non-zero. Now, we've looked at some graphs already of polynomial functions, but I want to explicitly say some of the features of polynomial function graphs. First off, the graphs of polynomial functions will always be continuous. There's a mathematical specific definition of continuous that involves limits, but the one that you probably know is the more common way to talk about continuous, meaning there's no jumps. You can draw the graph in one without lifting your pencil, right? Also, polynomial functions do not have sharp corners. By sharp corners, I mean like when we were dealing with the absolute value of x, it came to a sharp corner. That's what I mean by sharp corner at the vertex. So all polynomial functions, they may turn, but they're going to turn in a smooth way if you zoom in enough. The domain is going to be all real numbers. There's nothing you can't plug in into a polynomial function. So the domain is going to be all real numbers. Because the domain is all real numbers, we can always plug in x of 0 and find a y-intercept. So we're always going to have one y-intercept. Can't have two because then it would negate it being a function. Let me skip these next two. I'm saying end behavior, we saw that at the end of last time. The end behavior is that if x is going off to the right or off to the left, it's going to go up to positive infinity or negative infinity. One of the two. It's going to go up forever or down forever as we're moving to the right, and then up forever or down forever if we're moving to the left. Now, these two, the 5th and 6th points, are the ones that are most interesting that you might not have seen. If we have a polynomial function, which is degree n, so in other words, we're talking about this lead term being x raised to the nth power. Then that polynomial function has at most n x-intercepts. So if it's a 3rd degree polynomial, it can only cross the x-axis at most 3 times. If it's a 4th degree polynomial, it can only cross the x-axis at most 4 times. It could be less. If it's a 4th degree polynomial, it may never cross the x-axis. Couldn't cross the x-axis at 1 spot, or 2 spots, or 3 spots. But it's anywhere from 0 to n x-intercepts. And it's going to have at most n minus 1 turning points. Do you understand what I mean by turning points? That means from where we go from increasing to decreasing, or from decreasing to increasing. So when I talk about a turning point on the graph, let's say we have a cubic function that does something like this. This local maximum is a turning point. It's the spot where I go from increasing to decreasing. And this local minimum is a turning point. It's where I go from decreasing to increasing. So turning points mean going from increasing to decreasing. This is a rough sketch of a cubic polynomial function. And you can see that if we have a cubic polynomial function, if we have 2 turning points, then how many times can it cross the x-axis? Well, it could cross the x-axis if the x-axis is down here just 1 time. It also can cross the x-axis if the x-axis kind of goes right there, hits that point. Can cross at 2 spots, or hit it at 2 spots, I should say. Or it could cross the x-axis, if the x-axis is right there, cross it at 3 different spots. But that's the maximum. If you have 2 turning points, then it can cross at most at 3 spots. And maybe it hits it at 2, maybe hits it at 1. This one actually can't do a 0 because the end behavior, one side goes to positive infinity and one side goes to negative infinity. So the end behavior doesn't let me never cross the x-axis. It always has to cross the x-axis at least 1 spot. But in this case, it could cross at 1, 2, or 3 spots. So that's where this is going. Or that's what we're talking about when we're talking about x-intercepts. Turning points are those local minimums and maximums where we change from increasing to decreasing, or vice versa. Right? So that's what this says. That's what this slide says. Turning point is the point where the function turns from increasing to decreasing, or vice versa. Now, we've already seen that the end behavior of a polynomial function is the same as the end behavior of its leading term. So the term with highest degree is determining the end behavior of the polynomial function. Let's do a couple of examples where we just graph using technology and look at the graphs of these functions. So we'll take x squared minus 2x minus 3 and x squared plus 2x plus 10. I'll do this on Desmos. You can also do this on your graphing calculator as well. Whoops. I'm going to put that over to the side. That over there. Good. All right. So as you can see, this is the f of x, which is equal to x squared minus 2x minus 3. Notice that this is a second degree polynomial. It's quadratic, so it's degree 2. That means it can cross the x-axis at most 2 spots, which this one does. This one crosses the x-axis at 2 spots. 3, 0, and negative 1, 0, obviously. It also can have at most 1 turning point. And it does have a turning point. Notice that this turning point is the vertex. So the vertex of the quadratic is the turning point. Okay. It crosses at 2 spots. Also notice that it's smooth. It's continuous. When I say smooth, I mean no sharp corners. So there's no sharp corners. It's continuous. It's a really nice graph. The end behavior, as you move to the left, it goes off to positive infinity. As you move to the right, it goes off to positive infinity. If you look at the other quadratic function, it's also a parabola pointing up, has no sharp corners. Where we change from increasing to decreasing is a nice smooth corner. I say smooth, like that. But notice that this one does not cross the x-axis. So while we have at most 2 x-intercepts when we're dealing with a quadratic function, it might be that there are 0 x-intercepts when you're dealing with a quadratic function. Maybe that there's 1. But here's an example where there's no x-intercepts. So don't think you're guaranteed 2 x-intercepts on a quadratic function, right? You're guaranteed 2 or less. Could be 2, could be 1, could be 0. Oh. Let's take a look at these two as well. X to the third minus x squared minus 2x minus 3. and negative x to the third minus 2x squared minus 2. Again, I'll graph this. Here's the nice thing about this. I use very similar concepts. So I didn't have to change much.
Question.
Thank you. So here's a cubic, and you can see, this is kind of why I drew on the board earlier. We see it's again a nice polynomial graph, smooth transitions, no sharp corners, domain is all with real numbers, continuous. Here we're ending up with 2 turning points. And while we could have at most 3 x-intercepts, in this case we only have 1 x-intercept. Only one spot that it hits the x-axis. By the way, you can easily see if you move that up a little bit, it can touch the x-axis at 2 spots. If you move it up a little bit further, it can touch the x-axis at 3 spots if you wanted to. Similarly with this one. Okay, this is a cubic, but with a negative coefficient on the x to the third. Okay. Any questions about seeing these graphs, what they look like? Something like that. Good. Now, on these polynomial functions, the y-intercepts are really easy to find. Y-intercepts, you just plug in x equals 0, and then you can compute what y is. There's only one of them, right? The x-intercepts are going to be the harder thing to solve, the harder thing to find. To find the x-intercepts means that we set y equals 0 and we solve that equation. Just as a notational thing, x-intercepts are points where we hit the x-intercept, hit the x-axis, excuse me. X-intercepts are the points where we hit the x-axis. So they all are of the form a comma 0. Because of that, that means when we plug in a into the function, we get out a 0. Okay. Another term that we can use that's kind of synonymous but not exactly the same as x-intercept is a 0 of the function. A 0 of the function is a number that you plug in to the function and you get out 0. So a is a 0 of the function if f of a is equal to 0. And if a is a real number, then this is also telling us that that's where an x-intercept is. If a is a complex number that has an imaginary part, non-zero imaginary part, it could still be a complex 0 or imaginary 0, but it wouldn't correlate to an x-intercept because in order to graph it, we need to have real number a for the x-intercept to be there. Does that make sense? So I'd say x-intercepts are almost the same thing as zeros. They are the same thing as zeros of the function when we have real numbers. X-intercepts are the points, I have a real number 0, then it is going to give me an x-intercept, right? But if you have a complex 0, then it's not going to lead to an x-intercept. It's going to lead to a complex number 0. So, like I said, in order to find these x-intercepts, we want to set y to 0 and then solve. One way we can do that is we can factor these higher degree polynomials. We'll see some other tools that we can use later, but for right now, with polynomial functions, we have to factor those polynomials. Does that make sense? Hold up. Sorry. Good. So we're going to factor polynomials in order to solve them. Okay? Now, when a polynomial is already factored, things work out really nicely. We have here f of x is equal to 3 times x minus 2 times x minus 4 times x plus 5. And then we have this other polynomial, g of x is equal to negative x times x minus 7 squared times x plus 1 times x plus 5 to the third. By the way, if you expanded this out, this would be a polynomial of degree 3 because we have x, x, and x. This would be a polynomial of degree, well, I get one x here. I'd actually get 2 copies of x here, then another 1, and then 3 copies. So 3, 4, 5, 6, 7. That'd be a polynomial of degree 7. If we are finding the x-intercepts, all I have to do is set 0 equal to this polynomial, which is already factored. And then use that 0 factor property to say, well, this means this would be true if any one of these 3 or 4 factors is 0. I say 3 or 4 because if I set 0 equal to 3, that's obviously not true, so that's never going to work. But when I set 0 equal to x minus 2, there's a time where that will work. If I set 0 equal to x minus 4, there's a time that will work. And then if I set 0 equal to x plus 5, there's a time where that would work. So we end up with 3 x values. Add 2 to both sides, you get x equals 2. Add 4 to both sides, you get x equals 4. Add negative 5 to both sides, you get x equals negative 5. So this tells me that there are 3 real zeros of f of x. So these are the zeros of f of x. These are the things you can plug into the function and it'll give you out a 0. If I want to turn these into x-intercepts, since they're all real, I just turn them into points. I go from x equals 2 as the 0 to the point 2 comma 0 as the x-intercept. X equals 4 is the 0, 4 comma 0 is the x-intercept. X equals -5 gives me -5 comma 0 as the x-intercept. So 3 real zeros, 3 x-intercepts. We're good to go. When you do that same thing with g of x, we would set 0 equal to -x times x minus 7 squared times x plus 1 times x plus 5 raised to the 3rd power. And so we can set 0 equal to the factor -x. We can set 0 equal to x minus 7. By the way, there's actually 2 copies of x minus 7 here. If I did 0 equals to x minus 7 again, you can see that I'm going to get the same value. So I don't need to repeat factors when I write them down as zeros and x-intercepts. Does that make sense? So I can just write down x minus 7 is equal to 0 once and be good with it. By the way, we say that this is going to have multiplicity too, because there's 2 factors of x minus 7. We'll talk about multiplicities in a little while, but x plus 1 is set equal to 0. And then again, I have 3 factors of x plus 5. I can just set x plus 5 equal to 0 once. This tells me x is equal to 0. This can happen when x is equal to 7. Again, divide by -1, add 7 to both sides, subtract 1 from both sides, and then subtract 5 from both sides. So I have 4 zeros. And if I'm finding the x-intercepts, then I have 4 x-intercepts, 4 real zeros, 4 x-intercepts. So 4 real zeros led to 4 x-intercepts. Interestingly enough.
It's a question, Professor.
Yeah.
So, yes, it's curious that they're not written in descending order.
Oh, that I didn't write them in descending order?
The original equation was descending order. I guess why is that?
Oh, they don't have it. So this equation, when we say write polynomial in descending order, that means after it's been multiplied out.
Gotcha.
So this has been factored, so there's no real need to write it in descending order. Now, when you write your answers on Moodle, yeah, in Moodle, they may ask you for like the largest number first, and then the next largest, and then the second to smallest, and then the smallest. So they may ask you for that in order. But yeah, at this stage, at the factored stage, doesn't matter which term comes first or second or third. Thank you. So once we have things that are factored, it's pretty straightforward to find the x-intercepts. when I don't have things that are factored, then I want to factor them. Let's look at a couple of examples here. These are pretty straightforward examples of factoring. We have x to the third plus 6x squared plus 8x as my f of x. And as my g of x, we have negative x to the third plus 2x squared plus 35x. So this is option, if it's not already factored, then we need a factor. Now on both of these, the nice thing is this is a third degree polynomial, and each term has a factor of x. So what I can do after I've set the f of x equal to 0, if I'm trying to solve this equation for x, I can factor out the greatest common factor of x. And that'll leave me a quadratic polynomial in the parentheses. Also, notice that the coefficient of that quadratic is a 1. So all I have to do is look for factors of 8 that multiply to give me 6, and therefore then I could factor that quadratic. You get what I'm saying there? So this is what we did previously. We factored quadratic equations to solve them. So we're going to factor that quadratic. 2 times 4 is 8. 2 plus 4 is 6. So those are my factors of this quadratic. We're going to take and factor that x squared plus 6x plus 8 into x plus 2 times x plus 4. And then we're off to the races in exactly the same way we were before. We set everything equal to 0, x is equal to 0, x plus 2 is equal to 0, x plus 4 is equal to 0. Solve all 3 of those to get my zeros of the polynomial. Hopefully that's all straightforward. Subtract 2 from both sides, subtract 4 from both sides. This one you don't have to do anything. And then the x-intercepts are just the points x value comma 0, where the x value are the zeros. So 0, 0, negative 2, 0, and negative 4, 0. Now, we can do the same thing with g of x, so why don't you try that on your own? Try to do the same thing. Find the x-intercepts. For this g of x function by setting the output equal to 0 and then factoring the right-hand side. All right, so on this one, when we factor out the greatest common factor, since this has a negative out front, I'm going to factor out the negative x out of that polynomial. That way, I'll be left with a positive x squared as my first term in the leftover. Does that make sense? It's easier to factor something if it has a 1 in front of the x squared, right? If I'm factoring a quadratic. But if I factor out a negative, I have to do it on all three terms. So that'll be a minus 2x and a minus 35 if I factor out a negative x. So I get factor out the negative x and you're left with x squared minus 2x minus 35 as your quadratic. And then we can look at factors of negative 35 that add to negative 2. Negative 7 times a positive 5 would multiply to give me negative 35 and add to give me negative 2. So I use those two factors. And my quadratic factors into x minus 7 times x plus 5. Now the negative x still is there, so we set all three pieces equal to 0. And if any one of those is true, then my entire output will be 0. So on this one, divide by negative 1, you get x equals 0. On this one, add 7, you get x equals 7. On this one, subtract 5, you get x equals negative 5. And then the x-intercepts are the corresponding points. 0, 0, 7, 0, negative 5, 0. So this is one option for factoring. And it's basically you pull out the greatest common factor, and then what's left over is a nice quadratic that we've dealt with before. Right? So we've pulled out the greatest common factor, and we're left with a quadratic that we can factor using the method we looked at in one of those previous sections, right? Quadratic equation. So that's one option for factoring. We're going to look at another option for factoring as well with these two examples. Here we have a function f of x with 4 terms, all which are unique, so there's no like terms there. And we'll get the same thing with g of x. We'll have a function with 4 terms where none of them are like terms. So f of x is equal to x to the 3rd plus 7x squared minus 3x minus 21. And then we get that g of x is equal to 2x to the 5th minus 9x to the 4th plus 10x to the 3rd minus 45x squared. Yeah, we're good. So we're going to find the x-intercepts. So we're going to set the output equal to 0, and then try to factor the right-hand side. This right-hand side is a cubic polynomial. And on f of x, this one here, there's no greatest common factor. There's nothing I can pull out from every single term. So I can't use the greatest common factor here, like I did in the previous example. But what I can do is I can match these up or pair these up in this case. Now, this is not going to work for every cubic that you run into. But in this special case, if I look at this pair and this pair, after I pull out the greatest common factor of this first pair, the greatest common factor will be x squared of the first pair. I'll be left with x plus 7. The greatest common factor of the second pair is a negative 3. And if I pull that out, I'm also left with an x plus 7. Bear with that. So in this case, if I look at first pair, second pair, and I pull out the greatest common factor of the first pair, greatest common factor of the second pair, I get x plus 7 and another copy of x plus 7. Now, if somebody said we had x squared times some number a minus 3 times some number a, what we could do is we could factor out the a. We could say that's like x squared minus 3 times a. They follow that? So factor it out. I put it on the right this time. Could have put it on the left. It really doesn't matter. But that's what we're going to do here with this x plus 7. It's just a number. X plus 7 is a single quantity. And so I can factor that out in the sense of I can say this is going to be x squared minus 3 all times the number x plus 7. Now, if this was a messy thing, then I may try to factor it more. But for right now, this is a pretty easy thing to deal with, x squared minus 3. So we'll set that equal to 0. And then we'll set the x plus 7 equal to 0. Notice again, I'm doing that because I have something times something equals 0. So I can use that 0 factor property. If I were to solve this, I would get 3 is equal to x squared. That means x could be equal to the positive square root of 3, or x could be equal to the negative of the square root of 3. We've done that trick before. It shouldn't be too crazy. And then over here, the only option is x is equal to a negative 7. So this gives me 3 different zeros. One at square root of 3, one at negative square root of 3, and the other at negative 7. All of those are real numbers. So that means I have 3 x-intercepts. One at square root of 3 comma 0, the other at negative square root of 3 comma 0. And the last at negative 7 comma 0. Now, like I said, this is a unique cubic function. This is a unique cubic polynomial function. Not every time are we going to have this pairing trick work. And this time it did, but it doesn't always work. But it's nice when it does. When it does work, it's nice. We say, pat ourselves on the back and move on, right? Now for this function, if I'm trying to find the x-intercept, I'll set the left-hand side equal to 0. Before I do this pairing trick, what I would do is I would factor out the greatest common factor first. Okay. All of these terms have a factor of x squared. So I'm going to factor out an x squared. And then I'm going to have 2x to the third minus 9x squared plus 10x minus 45 left over in parentheses. And then I can do the pairing trick on my cubic equation in the parentheses. Make sense? Again, this won't work every time, but in this case it does. Now be careful, if you want to write this as a bracket so you know what's going on, that's fine. When I factor out greatest common factor, that'll be x squared, and I'll be left with 2x minus 9. Greatest common factor here is 5. And then I'll be left with 2x minus 9. You see what I did there? This x to the second power has to stay in front. This one does. I have to kind of simplify what's inside here before I deal with that. So I get 0 is equal to x squared, and then I'll factor the 2x minus 9 out. So we're going to get x squared plus 5 times 2x minus 9. That's what's happening inside. I don't have to put another parentheses around. That's fine, just the way it is. Okay with that? And now set each piece equal to 0. I'll set it equal to 0 this way. X squared is equal to 0. X squared plus 5 is equal to 0. And 2x minus 9 will set equal to 0. To solve this one, we take the positive and negative square root of 0. That's just 0. So we get x equals 0 here. Only answer. For this one, we'd have x squared is equal to a negative 5. If I take the square root of negative 5, I get an imaginary number. Root 5 times I. Or I times root 5. Or negative I times root 5 if I take the negative square root of that number. So we get x is equal to negative I root 5. X is equal to a positive I times root 5. So I got two imaginary zeros in this scenario. And for this one, we'd have 2x is equal to 9. Dividing both sides by 2, we'd get x is 9/2, or 4.5 as a decimal. All right, so we see we have 4 different zeros of this polynomial function. How many x-intercepts do we have? 2. Exactly, 2. The complex or the imaginary x's are not x-intercepts. All right, you can't graph those on the xy grid. So while we have 4 zeros, the ones that'll show up as crossing our x-axis or hitting our x-axis are just the real numbers. So the x-intercepts are just the ones with real number x values. Does that make sense? By the way, when in doubt, graph it. If we took our g of x, I gotta write it down, 2x to the 5th minus 9x to the 4th plus 10x to the 3rd minus 45x squared I get this graph. Notice that the 2 places where this graph hits the x-axis, it goes up and touches the x-axis at the origin and comes right back down. So that was where x was equal to 0. And then it crosses over the x-axis when x was equal to 4.5. And again, the complex zeros don't give me x-intercepts. I say complex meaning, obviously, the non-real complex numbers. So there you go. That's what it looks like. Crazy, this thing goes way, way down there before it kicks back up. Goes down past negative 400 before it shoots back up. So it goes way, way down. Let's see. There you go. All right, any questions about? Yeah.
For my graphic calculator, it just looks like a straight line and then there's one off to the right across y-axis.
Yeah,
Anyway.
it's probably the window. All right. Yeah, you can do this on the graphing calculator. Just have to make your window pretty small around this so that you can see where it's at. But if you graph it with the TI-84 calculator, use the right window, you'll see the exact same concept. You should see the same concept.
Plus, would you mind showing me?
Yep. Yeah, I can do that. In fact, I can do that right here. So let's try to. Get that up on the screen. So we go y equals, and then I'm going to plug in my equation. Oh no, spin that up. 2x to the 5th minus 9x to the 4th. 2x to the 5th. 9x to the 4th. and then plus 10x to the third minus 45x squared. So that was the graph. I kind of know what's going to happen. If I go zoom standard, which is zoom 6, you can see it goes up, down, and then crosses back over. At least that's what mine does. If you want to zoom in on that, you can either zoom using the box feature, hit zoom, and then if you use the box, you can kind of go to the upper left corner of the box, hit enter, down and to the right. And then you see it there too. And then you can trace. And you can see it hits right at the origin. And then if you hit 4.5, you can see it hits right there too. So same thing on the graphing calculator as Desmos. Just a little bit different how you deal with it. How you zoom in and zoom out. That stuff. Thank you. Yep. All right. Now, what if we can't factor? What if we can't find the x-intercepts using factoring? Well, we'll see some different techniques later on. In fact, the next couple of sections, 3.4, 3.5, 3.6, they're all about different techniques to finding these x-intercepts or these zeros of polynomial functions. But another option I can have, if I can't say that I know there's an x-intercept precisely when x is equal to 4.5, I might be able to say, I know there's an x-intercept somewhere between 4 and 5. And oftentimes in mathematics, we don't necessarily need an exact answer, but an approximate answer would be just as good, right? In a lot of applications, you might end up with these really weird, ugly functions. And knowing approximately where it hits the x-axis is what you really want to know. So we can find a range of x values or for our x-intercepts. We can say, I know that there's some x-intercept which has an x value between 4 and 5, instead of saying I know it's precisely at 4.5. And the way we do that is we utilize what's called the intermediate value theorem. Since polynomials are continuous, this is what the intermediate value theorem says. It actually says this for any continuous function, but in particular for polynomials. If we have a continuous function, and I know the value of f of b, and I know the value of f of a, then every value between f of b and f of a is going to have to be obtained by some point on the interval from A to B. That sounds really complicated, but it's actually a really easy concept. All right? Like I said, it sounds really complicated, but it's a really easy concept. Let's say we have a function f of x. And I know it goes through the point A, comma, f of A. And I know it goes through the point B, comma, f of B. So it goes through those 2 points. And I know it's continuous. If there is a horizontal line drawn somewhere between A and B, my function has to cross over that horizontal line. That's all it's saying. All right? Y equals some value. We'll call it y equals value. The intermediate value theorem says that because it's continuous, I can't do one of these things where I jump over the line. And because it's a function, I can't like go backtrack and do weird other stuff. So it's a continuous function, so no matter how I draw it, I have to cross that horizontal line to get from one point to the other. I might actually cross it in a couple of different spots, but I have to cross it at least once between those two values. I drew it this way, where the f of A was bigger, but it would work the exact same way if the f of B was bigger. All right? We just go left to right, we have to cross it the other way. From bottom to top. Okay. Does that work? So the intermediate value theorem says that. And you know what value we're going to use when we're looking for x-intercepts? We're going to, when we're looking for x-intercepts, going to look for the value to be 0. Because if I have y equals 0, that means I have to cross the x-axis. You okay with that? So that's it. We're just going to look for 2 places where one output is a positive, one output is a negative, and I'm going to know that that we cross the x-axis, right? So this is the intermediate value theorem, written a little bit formally. I'm writing it informally on the board, saying that it has to cross some horizontal line, any horizontal line that you draw between f of A and f of B. But this is the formal. If I have 2 numbers in the domain of a continuous function, which do not give me the same output values, then every value between f of B and f of A, so that means any horizontal line I draw, will be obtained on the interval from A to B. So I have to cross that horizontal line somewhere between A and B. You don't have to worry about the specifics of it. Just as long as you get the concept of it, we're good to go. All right. So let's take a look at specific numerical examples. Let's say I have a function and I know it's continuous. And I know f of 2 is equal to 14, and f of 5 is equal to 39. So we have 2, 14 as one point, and 5, 39 as another point. Is there a number x between 2 and 5 that forces my function to have output of 22? And then is there a number between 0 and 2 that gives f of x equal to 22? All right, how about the first one? Is first one yes or no? Yes. Yeah, that's a yes. This is the exact application of the intermediate value theorem. We're saying that we're looking for an output value, a y value, to be 22. Well, 22 is between 14 and 39. So I know that somewhere between x value of 2 and x value of 5, this function has to cross over. It might cross over at a lot of different times, but it has to cross over at least once. Okay with that? So yes is the answer to the first question. How about the second question? No, not necessarily, right? The second question is there an x such that f of x is 22 between 0 and 2? And the answer is no, not necessarily. There could be one, but it's not forced upon us. We know there's one between 2 and 5, but we don't know what happens to the left of that point. Maybe it goes down forever to the left, right? It could turn back up and cross 22, but again, it's not guaranteed to have a value there. We okay with that? So that's the intermediate value theorem. Try this one on your own. You can think of this as the same function. You can think of this as a different function. F of 7 is -2. F of 8 is 11. Between 7 and 8 gives f of x equals 0. -5. All right, so sometimes on these, well, not sometimes, most times on these, I like to, even drawing a picture, very, very nice, just because super easy to understand if you're looking at the picture. Sometimes on these types of questions, there's so much information that when you try to think through it in your head without drawing a picture, it gets jumbled. But when you draw a picture, it's pretty straightforward. We're looking for a number between 7 and 8, so between 7 and 8, where my output is 0. Well, 0 is between -2 and 11. In fact, it would be a little bit closer to -2 than 11. So y equals 0 is here. Do I have to cross it? Yes, I'm going to have to cross it, right? So the answer to this first one is yes. We are forced to have an x value somewhere between 7 and 8 that crosses y equals 0. That has an output of 0. So if this were a function, I would know that there is an x-intercept somewhere between 7 and 8. The next question says, is there an x such that between 7 and 8, my output is a -5? Well, the output of -5 is below both points. So it is perfectly reasonable to think that we may not cross that horizontal line between the values of 7 and 8. Are you okay with that? So the second one is a no. It's not guaranteed. It could happen, but it's not guaranteed to happen by the intermediate value theorem. Are you okay with that? Could happen, but not guaranteed. All right, so now that we know what the intermediate value theorem is, let's use it to get a close estimate for an x-intercept. Okay. So we're going to get a close estimate for an x-intercept for this function, f of x equals x to the third minus 2x plus x minus 1. Now, the first thing I'm going to do, it says, look for an x-intercept between x equals 0 and x equals 2. What I would do is I would plug in 0 into this function. When you plug in 0, you get an output of -1. We're okay with me not showing that to get an output of -1. When you plug in 2 to the third minus, oops, this should be 2 squared. I apologize, that should be 2 squared. Here it's right on notes. Oh, my bad. That should have said 2 squared. 2x minus 2x squared. I apologize. So that should have said minus 2x squared on the notes. Let's keep it that way. That's why we have 4 terms. So we have 2 raised to the third power minus 2 times 2 squared plus 2 minus 1. That gives me a positive 1. Since 1 has an output that is a negative, the 0 has an output that's a negative number, and the other number 2 has an output that's a positive number, I know that somewhere between 0 and 2, my graph is going to cross the x-axis. I'm going to write it this way. So for some x value, where x is between 0 and 2. Okay. Where would be your best guess? What would you try next? We saw plugging in 0 gave me a -1, plugging in 2 gave me a positive 1. Well, I'd probably go halfway between 0 and 2, right? So let's get a better estimate by narrowing our search. We have a big interval where we know there's going to be an x-intercept. Let's make that interval smaller. Okay. Use prime, middle value, x equals 1. So we go f of 1, and then we do 1 to the third power minus 2 times 1 to the second power plus 1 minus 1. That gives me out a negative 1 as well. Everybody get that? How I'm getting up, just plug it in. Now, notice that let me write it over here. I'm going through the point 0, negative 1. I'm also going through the point 1, negative 1. And then I'm going through the point 2, 1. And the whole time, we're comparing that to where the x-axis is. Right? So earlier I said that since this point is below and this point is above, there has to be some crossing value in between those. But notice now I can shift my start point over to 1 and my end point over to 2. Now I know that there has to be some crossing point between x value of 1 and x value of 2. They follow that? Again, because of intermediate value theorem. So we tried the middle value of x equals 1. It gave us a negative, so I'll use the positive output from the previous example. We still know that f of 2 is 1 from the previous example. So we must have an x-intercept with x value between 1 and 2. And you know what I do if I want to get even a better approximation? And say, let's go halfway between 1 and 2 and see what happens. So we'll try the middle value of x equals 0.5. So plug in 0.5 into there. Oh, 1.5, yes, you're right. 1.5. Sorry, instead of 0.5. I think I was thinking between 0 and 1. So 1.5, yeah, 1.5 would be the middle value between 1 and 2, not the middle value between 0 and 1. So 1.5 is what I plug in. Sorry. Good call. Good catch. 1.5 cubed minus 2 times 1.5 squared plus 1.5 minus 1. That would give me a negative 0.625. Is that what everybody else got? So that's closer to the x-axis, but still underneath, right? So I'll use the positive output value from the previous. And then I say we must have an x-intercept between, or with x value between a 1.5 and a 2. And you can do the same thing now again for 1.75. That'd be the middle value between 1.5 and 2. And then you can do middle value between 1.75 and 2 with the next one, and so on and so forth. And if you ever do crossover, then you would use just the first one that's negative and the first one that's positive, the closest to. Does that make sense? In other words, if our 1.5 had given us a positive point, a positive output value, then I'd go from 1 to 1.5 as my new interval. We get that? That makes sense. So we just kind of narrow that interval as much as we want. And you can do that process over and over and over and over until you get a really good approximation of the x-intercept. Now, I want to say something about that example. We don't typically do that a lot. Okay? With modern technology, with our graphing calculator, we don't do that a lot because our graphing calculator can approximate those values where it crosses the x-axis in a really efficient way. Okay. So we knew that some x value between 1.5 and 2 was going to be a 0 for our function. But with modern technology, I did the 1.75 as well, I forgot to say. But with modern technology, all we do is take x to the third minus 2x squared plus 1x minus 1. The exponent works here. We could graph that. And then we could use our calculate menu to find a 0 for that function. Calculate 0. It does kind of an approximation technique, kind of like the one we're doing here, not exactly the same, but. So we take a right bound, left bound, I'm looking for a 0 inside that interval, and somewhere in there. And sure enough, you can see the 0 happens at about 1.7548777. So with modern technology, we don't have to use the intermediate value theorem as much. We can get good approximations just by asking technology to find where it crosses the x-axis. That work? So we're not going to do that a lot. You should know about the intermediate value theorem, but like I said, that's not much more efficient to just trust a little technology with that. Does that work? Okay. So the last part of today is on dividing polynomials. So we're trying to find the zeros and the x-intercepts of these polynomial functions. We'd like to do that algebraically as much as possible. We know we can get approximations with our calculator, but we'd like to get exact values as well. And one of the techniques that helps us do that is by dividing. Now, the terminology I'm going to use is that if we take two functions and divide them, f of x divided by g of x means that the dividend is f of x and the divisor is g of x. So dividend and divisor. The quotient we call q of x, sometimes capital Q, sometimes lowercase q, doesn't matter, plus the remainder. That's the leftover piece. So dividend over divisor equals quotient plus remainder. It's not a big deal. You're not going to be tested on the language, but I'm going to use the language when I go through it. So that's all I'm saying. One option for division is using long division. Long division repeatedly asks, what do I need to multiply the first term of the divisor by to match the lead term of the remaining part of my dividend? It'll make a lot more sense when we do an example. But that's basically what you're doing over and over and over again. What needs to multiply the first term of the divisor to match the leading term of the dividend? And then I multiply that divisor but by that term that I think, and then subtract the resulting polynomial from the remaining dividend. That's a mouthful. Okay. Many of you, I'm sure, have already seen long division by polynomials. So let's just go through an example. We have x to the third plus 5x squared minus 8x minus 10 as the dividend, and the divisor is going to be x squared plus 3x minus 4. And I want to divide those two polynomials. Long division would put the divisor out front and the dividend underneath the long division sign. And then I ask, what do I multiply the lead term of the divisor by to match the lead term of the dividend. And you said, what do I multiply x squared by to get an x to the third? You would have to multiply by an x. So you write that up there. Now you don't take the x just by the lead term. You have to take the x times the entire divisor and write it underneath. X to the third plus 3x squared minus 4x. And then what I do is I subtract that. You guys seen this process before? X to the third minus x to the third gives me no x to the thirds. That's why I wanted these to match up, so that when I subtract it, I drop this whole column. 5x squared minus 3x squared is a 2x squared. Negative 8x minus a negative 4x, that's like negative 8x plus 4x, gives me minus 4x. This is minus 10 plus or minus 0, so we just get minus 10. So I get this remaining of my dividend. This is the part of my dividend that remains. Then I go through again and I say, what do I need to multiply x squared by to give it 2x squared? That's just 2. So I multiply, I write plus 2 up there because I need it to be a positive 2. And then I multiply all of these by 2. 2x squared plus 6x minus 8. And then I subtract. And again, the reason why we wanted these two terms to match up is so that when we subtract, we get rid of that entire x squared column. Negative 4x minus 6x gives me negative 10x. Negative 10 minus a negative 8, negative 10 plus 8 gives me minus 2. So negative 10x minus 2 remains. Now this part that remains is of lower degree than my divisor. Therefore, I'm going to stop at that point. Anything that I multiply x squared by now to get negative 10 times x is not going to be a polynomial term. So that means when I take this polynomial and divide it by this polynomial, I end up getting x plus 2 with remainder negative 10x minus 2. If you wanted to be really fancy about that, I didn't leave myself enough room, but that's okay. You could have also written this as x plus 2 plus a negative 10x minus 2 over my divisor of x squared plus 3x minus 4. So I could have written that as a fraction of negative 10x minus 2 divided by my divisor. So that's long division. Okay. We will use this long division in a couple of examples in section 3.6. once we get to it. Or maybe just one example, can't remember now. One example, 3.6, maybe two examples. So that's why we kind of need it right now. Now, on the other hand, in this situation, in our example 1, we divided by a quadratic. Okay. Most of the tools that we're going to need are going to be dealing with linear pieces. So we'll need to be able to divide by a quadratic in maybe 1 or 2 examples in 3.6, but most of the division that we're going to do is going to be dividing by a linear piece, something like x minus 2. I'll do this just once through long division. I'll show you what we get there. So we go x minus 2 as my divisor, x to the third plus 5x squared minus 8x minus 10 as my dividend. And we use long division. To divide. Okay? So I say, what do I need to multiply x by to get x to the third? That's going to be an x squared. When I multiply x squared by these 2 terms, I get x to the third minus 2x squared. And then I subtract. This first column goes away, and I end up with 7x squared minus 8x minus 10 as the remaining part of my dividend. Then I say, what do I need to multiply x by to get 7x squared? That's going to be a 7x. 7x times x minus 2 gives me 7x squared minus 14x. Subtract that. Negative 8 plus 14 is a 6, so we get 6x minus 10. And then I ask, what do I need to multiply by? To get 6x, I need to multiply by 6. So that's a positive 6. 6 times x minus 2 is 6x minus 12. Subtract that, and we end up with a positive 2. Negative 10 plus 12 is positive 2. This is a constant that's of degree 0. X minus 2 is of degree 1. So now I have degree of my remainder less than degree of my divisor. So I stop. So that means that doing this division gave me x squared plus 7x plus 6 plus remainder, or with remainder, of 2. Or we could have written that as x squared plus 7x plus 6 plus, we could have put our remainder over x minus 2 if we would have liked. Are you okay with that? So that's division. That's long division. And if you get good at this, you can do some problems really quickly. You can do long division on something like this, I'm not going to do example 3 using long division. But you could do example 3 using long division if you wanted to. It would take you a bunch of steps. You'd start with an x to the third term and then get an x squared term and then so on and so forth. All the way down until you got your constants. But I want to introduce a new type of division. Maybe not new to some of you, but new to this class. The other type of division that we can use is called synthetic division. It's only going to work when the denominator looks like x minus a number. I put x minus r. R is just a real number. Could also be a complex number, but it's much harder to do if it's complex. It has imaginary pieces. And this process is usually a lot quicker than long division. So we're going to have x minus r as my divisor. If I don't have x minus r as my divisor, then I can't do synthetic division. Okay. Has to have x minus r as our divisor. And synthetic division does this. If I have a polynomial divided by x minus r, I'm going to put the r out to the right, and I'm going to create a table. The top row of this table is going to be the coefficients of my terms in descending order. And then what's going to happen is I'm going to start on the left-hand side with a sub n, and I'm just going to drop it down. It's like adding 0. And then I'm going to take the r times that a sub n and put it right underneath the a n minus 1. And then I'm going to add those two numbers. And every time I move down, I'm going to be adding numbers. Every time I move up and to the right, I'm going to be multiplying by that r. Does that make sense? Again, this will be easier to see once we get an actual example. So let's take the example that I skipped, which was x to the 4th plus x to the 3rd minus 3x squared plus 4x minus 5. And that's all being divided by x plus 3. So in this case, and this is one of the things you have to watch out for. In this case, notice how our denominator is x plus 3. That means our r is a negative 3. Does that make sense? It's always of the form x minus r. So if I have a plus here, that has to be a negative 3. That's my r. So r is negative 3. I'm going to write it out sort of to the left. And then I'm going to write down the coefficients. By the way, some people do this. Some people put a box around that negative 3. That's fine if you like to do that. So then I write the coefficients. I'll write 1 as the coefficient of x to the 4th. 1 is the coefficient of x to the 3rd. Negative 3, 4, and negative 5. I need to make sure that they're in descending order. So I'm going x to the 4th, x to the 3rd, x squared. And then I don't miss any x to any powers. So they're all in descending order. And then I'm gonna put a space right here, and then I put a line. The first thing that I'm going to do, every time I move down, I'm going to be adding. So the first thing I do is move down. 1 added to nothing is 1. Then I'm going to move up and to the right by taking a -3 times this 1. That creates a -3. Then I'm going to move down again. 1 plus -3 gives me a -2. I'm going to take that -2 and again multiply it times a -3. I'll write that as. When I do that, -3 times -2 gives me a +6. And then once again, I move down by adding. So I add, that gives me a +3. -3 times +3 gives me a -9. Four plus -9 is a -5. -3 times -5 is a +15. And I'd be left with 10 in my final spot there. What this is implying we started with coefficients of x to the 4th, x to the 3rd, x squared. We did this division step. What this is telling me is that my quotient is going to start out with a 1x to the 3rd. It's going to drop down one exponent of x. Does that make sense? We started with x to the 4th down here, meaning my quotient is going to start with x to the 3rd. So this is going to be equal to 1x to the 3rd minus 2x squared plus 3x minus 5. And this 10 is my remainder. With remainder of 10. Okay. So while I started with like x to the 4th, this is my x to the 3rd term, this is my x squared term, this is my x term, this is my constant term. Now, dropping down here, this is my x to the 3rd term of the quotient. This is my x squared term of the quotient. This is my x term of the quotient. This is my constant term of the quotient, and this is my remainder. If that makes sense. Once you get used to that, it's a really quick process. It's a very quick process once I get used to it. It takes a minute to get used to the adding and multiplying. But if we compared that to the amount of time that it would take to do long division on this problem, the synthetic division is much, much quicker. And in fact, you can do really large problems using synthetic division pretty quickly. So let's do this example. I'll walk through it. We have x to the fifth minus x to the third plus 2x squared minus 4x plus 9, all divided by x minus 2. All right. There too. Now, the thing we have to be careful for in this case is that when I start writing coefficients, a lot of times people have a tendency to write 1 and then immediately afterwards write a negative 1. Okay. This 1 is the coefficient of the x to the fifth term. The next term I need is the coefficient of the x to the fourth term in my dividend. Obviously, there's no visible x to the fourth term in my dividend, and therefore, I need to make sure I put a 0 there as a placeholder. If I don't put that 0 as a placeholder, I'll be all thrown off when I get down to my quotient. Right? So if you are missing a term, like missing an x to the fourth term, that's just a 0 x to the fourth. And then we can go on from there. Then I can go to my x to the third term, which has coefficient -1. Usually I don't write this on top, but I will right now. Then x to the squared term, that's a coefficient of 2, then -4, and then a 9 as my constant. And when we do this process, again, I just go through 1 drops down, 1 times 2 is 2. Oh, notice that this is x minus 2, so I'm using a positive 2 as my r, right? We follow that. X minus r, it's always x minus r. So x minus 2, I'm using a positive 2. So 2 times 1 is positive 2. Add those up, you get 2. 2 times 2 is 4. Add those up, you get 3. 2 times 3 is 6. Add those up, you get 8. 2 times 8 is 16. Add those up, you get 12. 2 times 12 is 24. Add those up, and you end up with 33. Okay. Okay, follow that? So it's that quick when you can do it. So multiply by 2 on the bottom, put it there. Multiply by 2, multiply by 2, multiply by 2, and then just add. And that means the division of this becomes, remember we started with x to the fifth here, we're going to start with an x to the fourth term in my quotient. So we're going to get 1x to the fourth plus 2x to the third plus 3x to the second power plus 8x plus 12 with remainder of 33. Or you could write that as plus 33 over x minus 2 if you'd like. Notice how quick that is once these things get big. Once these polynomials get big, this synthetic division can go really quickly still. Whereas long division, it takes a lot longer. I want you to try one problem on your own. Try to divide x to the third minus 9x squared plus 9x plus 10 by x minus 2. So we're using the same divisor, different dividend this time. And try to use synthetic division to do this. All right, so I'm going to go through this. One drops down. One drops down. Then I was going to say multiplies by 2. I'm thinking multiplies by 2 and right 2. So 1 drops down. Then I multiply by 2. 1 times 2 is 2. Add those, you get a -7. 2 times -7 is a -14. You end up with a -5 when you add those. 2 times -5 is -10. And when you add that, you get a 0. Everybody else get that same thing? All right. So what this means is that when you do this division, you end up getting, remember we dropped the exponent by 1 with quotient. That's 1x squared minus 7x minus 5 with remainder 0. In other words, you just get that. Everybody okay with the synthetic division? Yeah. Now, there's actually 2 things to see in these 2 problems. Okay? The first is over on both of these. Let's imagine, this is on the next slide, but I'm not writing it down, okay? So if you want to, I won't flip back to the slides, but this is what's going to be on the next slide. Imagine we have a function which is the dividend. So the output function, let's call this f of x, as x to the 5th minus x to the 3rd plus 2x squared minus 4x plus 9. And then we'll have this function as the dividend, I guess I'll call that one different. Let's call that h of x, just so we have something different on the board. If I plug in the number 2 into this function, take 2 to the 5th minus 2 to the 3rd plus 2 times 2 squared minus 4 times 2 plus 9. Do that on your calculator. What number did you end up with? 33, right? We ended up with 33. Which was our remainder. What if I plugged in 2 into the function h? 2 to the 3rd minus 9 times 2 squared plus 9 times 2 plus 10. Again, you can type that on your calculator. I ended up with a 0, which was my remainder. So that means, well, this doesn't guarantee it, but it is going to be guaranteed. All right. Whenever you're dividing by 2 minus some number, I misspoke. Whenever you're dividing by x minus some number, the remainder that you get out is going to be the same thing when you plug that number into your dividend. Okay, I divided by x minus 2 here. I got a remainder of 0. That's the same thing as what I get when I plug in a 2. Okay. And we'll go over this more in detail next time. But that tells me if I have a factor of x minus r of my polynomial, then the polynomial function is going to have a 0 when I can divide and get remainder 0, which means that the dividend is a factor of, the divisor is a factor of the dividend. Does that make sense? Again, we'll go over this more next time, but I just want you to know that when you divide, your remainder is the same thing you get out when you plug in that r value into the function. Okay. All right. We'll pick back up next time on this concept, and we'll see how we can use this to get all of the other zeros of our function. Okay. All right. I'll see you next time.